Alright, hello everyone. I hope all of you are doing great. So today we are going to be discussing the solutions to Google Kickstart round E 2022. This round ended like an hour ago. And talking about the round, I think it was a pretty good round. For the first two problems, I think they were a bit on the easier side as compared to a normal Google Kickstart round. But the last two problems were definitely good. And I think problem C was pretty apt for its position, whereas problem D was also like good for its position. It's definitely a bit harder than the problem D from recent Kickstart rounds, that is 2022 round D and C. I mean, in 2022 round C and D, the last problems were like considerably easier, but this time they have not done that. So this time they have kept the difficulty level at par with the previous Kickstart rounds of 2021, I could say. So yeah, this time the last problem was not very easy, as I mean, comparatively it was not very easy as compared to the previous rounds of this year, right? Anyways, so we'll be discussing the solutions to the first four problems, that is all the problems and all the test cases. So without any further ado, let's start with the first problem. Cool. So this is a pretty simple problem. Here, the problem statement says that John is playing a computer game, and in this game there are n cells which are aligned from left to right and are numbered from 1 to n, obviously. And initially all the cells are white. Now a cell is valid if it has a white color and it does not share any border with any adjacent red colored cell. So yeah, a cell is valid if it is currently white and it is not adjacent to any red cell. So on each turn, a player will paint any valid cell with the red color, and the game ends when there are no valid cells which are present to be painted. And the score of a player is equal to the number of cells that they paint. So yeah, so John is playing this game against the bot. So what happens is the bot will it is like poorly trained, and it is always choosing to paint the first valid cell from the left, right? So it scans the array from left to right, it finds out the first cell which is valid, and then it paints it red. Whereas John on the other side is playing the game carefully and he chooses any valid cell, right? So his choice is not dependent on any algorithm. Now the bot will make the first move and the players will then take turns alternatively. So what we have to do is we have to find the maximum achievable score by the bot, assuming that John is optimally playing to minimize the score of his opponent, right? So what John will paint will be in our hands and we will try to minimize the score, whereas the bot will try to maximize the score, but it doesn't really matter because the bot has a fixed algorithm using which he is painting the cells. So it essentially boils down to us trying to minimize the score of the bot. And the solution here ends up to be pretty simple. So let's just have a look at the solution. So the solution is just a very simple greedy algorithm. So at each step, we will basically try to block the maximum number of cells to be chosen by the bot, right? So we will try to block the maximum number of cells that can be chosen by the block. And since the block has a fixed algorithm using which it is choosing the blocks to paint red, then this greedy algorithm will always work, right? So let's say we have a situation like this. Currently we have the array like this, and initially all the cells are white, as we know, right? So now in the first turn, what happens is that the bot has the first turn and he will just choose the leftmost cell which is valid, which is nothing but the first cell. So he will choose this cell and he will paint it red. So this is done by the bot. But now it's our chance. So what we'll do is we'll try to block the maximum number of cells. So first we try this cell, and what we realize here is that this cell is already blocked because it shares a border with a red cell, that is it is adjacent to a red cell. So we will not paint it, right? Then we look at this cell. So if we paint it, then we'll be able to block this cell as well as this cell, right? Because both of them are adjacent to it. But we notice that this left one is already blocked. So this doesn't seem to be the optimal thing to do here, right? So we will not block this cell as well. Now we'll look at this cell. So now the good part here is that if we paint this cell to be red, so if John paints this cell, then this cell gets blocked as well as this cell gets blocked, and this cell is already blocked. So if we paint this cell, then we are getting a benefit of 3, which is the maximum benefit that we can get. So we can always do that, right? So this is the optimal thing to do. Okay, makes sense. Cool. So now what we have so what we have achieved is we have achieved a state like this, and now the game will just continue like it was going on before. So the next thing that would happen is that the bot will choose this particular cell because this is the leftmost cell which is not blocked, and then we will again leave two cells, and then in the third cell we will block it by John, right? So we will just keep doing this. So yeah, this completes the solution. This is the greedy solution that we have here. So an O1 solution is also possible for this problem if we just analyze the differences here. So John is always putting a block at a difference of 2. He's painting the block at a difference of 2, whereas the bot is painting at a difference of 1. So we can try to find out a greedy mathematical formula here, O1. But that's not really required, because if we have a look at the constraints allow us to have a O of n solution. So we can just greedily simulate this process, which is what I did. So yeah, this completes the solution. Let's just have a look at the code now. So the code is pretty simple. So this I denotes the current number of turns. So the turn, if I is odd, then that means it is the bot's turn, otherwise it is John's turn. So if it is the bot's turn, as you can see, he leaves a difference of 1. So if the previous painted cell was if the previous painted cell was last, then it becomes last plus 2. So if this is greater than n, then we simply break out. If that's not the case, we increment our answer and assign last to cur. Otherwise, it's John's turn. So as you can see, John is always inducing a difference of 2. So cur becomes last plus 3, and we do the same thing. If cur is greater than n, then we break out. Otherwise, we simply assign last equal to cur. I agree that there is a very simple O1 formula as well for this problem, but I think if the constraints are small, why risk it and just simply simulate the process, right? So yeah, this completes the solution to problem A. Moving on, let's try out the second problem now. And yeah, so this is what I was talking about. This problem is like really simple. I think it's much easier than problem A as well. So you don't really have to apply any logic here. If you have basic experience in competitive programming, you will just read the problem and you will know the solution, right? So there is basically a group of n students, and we have to assign a mentor to each student. So the mentor of a student is also obviously going to be a student, and every student has a rating. So the ith student has a rating of Ri, and what we have to do is we have to assign the assign the ith student a mentor j, such that rj is less than or equal to 2 times ri, and rj is as long as possible, right? So rj is as big as possible. That's what we want. Yeah, so this is the only requirement. We need the maximum value of rj, which is less than or equal to 2 times ri, where j is not equal to I. That's the entire problem. So this is the problem, and there are various ways you can solve this. You can solve it using binary search, you can solve it using 2 pointers, you can solve it using some data structures, which is what I did. So let me just quickly go over the solution. So what you can do is, so we can basically keep all the rating values in a multiset or a set. So we can keep all the rating values in a set of the form ri comma I. So we will have a set of pairs which will store the values ri comma I. So this set will contain exactly n elements. So to find the answer for the ith person, what we'll do is we'll simply remove this pair ri comma I from the set, and we'll simply take the lower bound of 2 times ri. So what we'll do is we will remove ri comma I from the set, and then take the lower bound of 2 times ri, right? So this can be found out in O of log n time. So this problem gets solved in a time complexity of O of n log n, which is good enough for the constraints, I guess, right? So yeah, this completes the solution to this problem. Let's just have a look at the code. Pretty simple here, nothing fancy going on. Yeah, so so another thing here is that if we cannot assign a mentor, then we have to simply output -1. So yeah, the code is pretty simple. What we do is we simply insert these values ai comma I in a set, and then for the ith element, first of all we erase ai comma I, and then we go over the upper bound of 2 times ai, and then we subtract 1 from it, right? Yeah, so we don't have to go to the lower bound, we have to take the upper bound. Sorry for that. Yeah, so we just take the upper bound of 2 times ri, and then we go one step backwards from it, so we get the maximum element which is smaller than or equal to 2 times ri, right? Makes sense. And once we found the answer for the ith element, we have to insert ai comma I back into the set, obviously. So yeah, this completes the solution to problem B. Pretty simple, nothing fancy going on here. So yeah, I think problem B was much easier than problem A also. I mean, both of them were really simple, but B was like very standard. That's the difference. Okay, moving on to problem C now. Okay, so this has a short problem statement, which is good. So we are given a palindrome string P of length n consisting of only lowercase letters of the English alphabet. What we have to do is we have to find the shortest non-empty palindrome string Q such that the string P concatenated with the string Q forms a palindrome as well. Right, so both P and Q are palindromes. P is given to us, Q is something that we have to find. So we have to find the shortest non-empty Q, which is a palindrome and which concatenated with P also forms a palindrome. Right. So yeah, the constraints for test set 2 are big. It's 10 to the 5, so we have to work upon an O of n solution. Although if you read the analysis of this problem, you will also find a solution which works in O of n root n. And I have some friends who actually did this and passed the test cases. But we are going to be discussing the most optimal solution here, which is O of n. Okay, makes sense. So let's start with the solution. Cool. Yeah. So what we want is we will basically try to find the shortest possible length such that there exists a palindrome string Q such that PQ is a palindrome. So we will try to find the shortest length X such that there exists a palindrome Q of length X such that PQ is also a palindrome. Right, so our target is to find the shortest value of X. Once we know the value of X, we will easily be able to find out the string Q, and we'll see how. Okay, so let's try for X equals to 1. So try for X equals to 1. So what's going on here? Let's see. So we have a string which is P1, P2 up till Pn, right? Or let's say P0 up till Pn minus 1. So we have this string P0, P1, P2 up till Pn minus 2, Pn minus 1. Something like this, right? Cool. So what we want is we are trying to have a string Q of length 1. So if we concatenate P with Q, what we'll get is we'll simply get Q0 here. And we want this Q0 to be a palindrome as well as the string from P0 to Pn minus 1 concatenated with Q0 to be a palindrome. So let's see what we want here. So for this entire string to be a palindrome, the first condition is that P0 should be equal to Q0, obviously, and P0 should be a palindrome, and then we have the rest of the string from P1 to Pn minus 1, which should also be a palindrome, right? So let's write it down. So P0 is equal to Q0, and P from 1 to n minus 1 should be a palindrome. Right, pretty obvious. And we also want that Q0 is a palindrome. So the string Q to be a palindrome, but since Q has a length of 1, it is always a palindrome. But we can still write it down. So Q is a palindrome. So this is not really a condition. This is something that we can always do. So I'll just erase this. So the two conditions that are here is that P from 1 to n minus 1 should be a palindrome, and P from 0 to 0 should also be a palindrome, right? Okay, makes sense. Now let's try for X equals to 2. So if we try for X equals to 2, what we'll realize is that again we have the same thing. We have P0, P1, P2 up till Pn minus 2, Pn minus 1, then we have Q0, then we have Q1, right? We have something like this. So here we want this entire string to be a palindrome, obviously. So what are the conditions for that? So first of all, we want this Q0 to Q1 to be a palindrome. We want Q to be a palindrome, obviously. And then we want P0 to be equal to Q1, P1 to be equal to Q2. And then we want this rest of the string to be a palindrome, right? So let's write down the requirements again. So the requirements are simple. So we want the string from P1. So we want the string from, P2 to Pn minus 1. So P from 2 to n minus 1 should be a palindrome, and uh, p from 0 to 1 should be equal to q from 1 to 0, right? In the reversed order, that's what I mean. And also q should be a palindrome, right? This is a requirement of the problem, that q should be a palindrome. But if q is a palindrome, then we know that q from 1 to 0 is equal to q from 0 to 1, so we can just replace it by q from 0 to 1, right? So in a sense, what we want is, so if q should be a palindrome, we know that q is equal to p. Q is equal to p from 0 to 1. So we want p from 0 to 1 to be a palindrome, and also p from 1 to n minus 1 to be a palindrome. So if you try to do this for x equals to 3 and x equals to 4, you will realize that this is the general case. So the general requirements are these. So the general requirement of the problem for an x to be valid is nothing but the prefix from, so we want x is equals to the smallest I. So x is the smallest I such that p from 0 to I minus p from 0 to I is a palindrome, and p from I plus 1 to n minus 1 is also a palindrome. So these are the general requirements of this problem, and this will be x minus 1 obviously, because we are taking 0 based indexing. So x is 1 plus, so 1 plus the smallest index I such that p from 0 to I is a palindrome, and p from I plus 1 to n minus 1 is a palindrome. Now the brute force solution is pretty simple. What we can do is we can generate all the prefixes and all the suffixes, and for every I, check on the prefix from 0 to I and the suffix from I plus 1 to n minus 1, and check if it is a palindrome or not in O of n time for every prefix. But since there are O of n prefixes, the total time complexity would be O of n square, which is good enough to solve the first test set, but unfortunately not the second test set. So we just have to do this quickly. This is the requirement. We just have to find this out quickly. And it turns out that there is a very simple way we can do that. So there is this algorithm called as the Mannekers algorithm. So Mannekers algorithm, or the Z function of a string. So basically this thing can be used to test whether every prefix of a string is a palindrome or not, also whether every suffix of a string is a palindrome or not. Basically the definition of a Z function is that the longest prefix of the array, which is also equal to the suffix starting from the position I, but I won't be going into the detail of Z functions. So if you want to read about this, this is a pretty useful string algorithm, and this is sometimes combined with an algorithm called as the KMP string matching algorithm. So these both are pretty important algorithms. So if you want to read them, I think a very good resource where I have learned this is nothing but CP algorithms. So you can just go to CP algorithms. You will find out a code template as well as the explanation of the algorithm. So I have taken up the code also from CP algorithms only. So yeah, I think CP algorithms is good enough to learn this. So using Z function, basically what we can do is we can check for every prefix of a string whether it is a palindrome or not, and we can do the same thing for every suffix. So once we do that, we can just verify this and find the smallest such I, and then our problem is solved. Once we have x, we know that p from 0 to I should be equal to q from 0 to I, and so the answer will be nothing but the prefix of length x, right? So what we have to do is find x using Z function, and then answer is p from 0 to x minus 1. And how to find x using Z function, that is again pretty easy. You first find all the prefixes which are palindrome, then find all the suffixes which are palindrome, and then just check for an index I whether a prefix as well as suffix is a palindrome or not, right? So yeah, if you want to know how to use Mannekers algorithm, then just go to CP algorithms and you will find out how to exactly implement stuff. Cool. So this completes the solution to problem C. Let's just have a look at the code. So this is just the code for Z function. I have taken this up from CP algorithms. You can go and check that out. So what I do is, first of all, I take in both the strings. I take in the string, and then I convert these strings to two strings, str1 and str2. So this is a standard way using which we apply Maneker's algorithm. I have used the question mark as a separator. So a separator is just a character which doesn't appear in both these strings. So these are just the implementation details of z function. So I find the z function for checking the prefixes whether they are palindrome or not, and for the suffixes whether they are palindrome or not. And then I simply find out the length of the smallest prefix, which is a palindrome, and the answer will be nothing but the prefix of the string s of length x minus 1. Right. So yeah, I hope this makes sense. This completes the solution to the third problem. Let's now move on to the last problem, problem D. Cool. Actually, I got two wrong answers here because I missed a very common thing. So this is something that they have mentioned here also, that if you divide -1 by 4 and take the floor, then it won't be 0, it would be -1. So for negative integers, the result of division, the result of integer division is ceiling, other than ceiling and not floor, right? So that is something that I missed. So yeah, if you also got wrong answer and were wondering why, this could be a possible reason. Anyways, let's have a look at the problem. So the problem statement is pretty involved, so I'll just simplify it for you guys. So basically what's going on is that we have a grid, and it is an n cross n grid where n is small. As you can see, the constraints on n are only 10, and we are a pizza delivery boy. We are starting at a cell AR comma AC, and initially we have 0 coins with us. Okay, and we can obviously move in adjacent directions, and we can also stay in the same cell every minute. And we have m minutes in which we have to deliver p pizzas, which we have, and we also have the coordinates of the positions where we have to deliver each pizza, and we know that every pizza is at a distinct location, right? So yeah, this is the problem. And what happens is that once we move from any cell to a neighboring cell, there is something which happens to the number of coins we have. Right, so basically what happens is that there is an operator defined for every direction and a value defined for every direction. So there are 4 directions possible: north, east, west and south. So there is an operator defined for north and a value defined for north. So let's just say that for north the operator is plus and the value is 1. So if we go north, then the number of coins will always become, if we have c coins before, then we will always have c plus 1 coins. Similarly, if the operator here is asterisk, that is multiplication, and the value of k for north is 2, then if we have c coins at I comma j, then we go north, we will have 2 c coins, right? So this is what is going on. So that's one thing. But also another way our coins can change is that we come to a cell where we deliver a pizza. So if we deliver a pizza, then we get some coins, and for all the p pizzas, we know how many coins we will get if we deliver that particular pizza, and the location of that pizza as well. So this is all the information that we have. And now the problem states that you start from AR comma AC initially with 0 coins, and you can end at any position, but you have to deliver all the p pizzas in less than or equal to m minutes, and we have to find the maximum number of coins you can have after you have delivered all the pizzas, right? Yeah, so that's the thing. So we can start and we can end at any cell, that's another thing. And the time which we take should be less than or equal to m minutes. There are no other restrictions on the time being exactly m minutes, right? So yeah, this is the problem. Also another thing is that if we reach a cell where we have to deliver a pizza, we can still choose not to deliver the pizza, and we can come back to that cell later and then deliver the pizza. So that's totally our choice. So we can decide whether we deliver the pizza or not if we are on the current cell. So if it is possible to deliver all the p pizzas within m minutes, then we have to output the maximum number of coins that we can have after all the process has ended. And if it is not possible, then we have to simply output impossible. So for the first test set, the special thing here is that there are no pizzas. So you can simply forget about the pizzas. So the problem simply becomes that you are starting at a cell and you have m minutes. So you can travel in any particular direction for these m minutes, and you can end at any particular cell, and you just have to tell the maximum number of coins that you can have. And in the second test set, there is this added constraints of the number of pizzas. So you have to deliver these 10 pizzas as well. So yeah, let's tackle this problem from starting from the first test set and then optimize a solution to run on the second test set as well. That is exactly what I did during the round. Okay, so let's see. So there is one very important observation which is required to solve this problem, and let's see what that observation is. So one important observation. So observation is that if we are on a particular cell I comma j, and we currently have c coins, then we try to move to a neighboring cell, then basically, okay, I'll just write it down. So let's say there are two scenarios that we are currently on cell number I comma j. So we are at cell I comma j, and in the first scenario I have c1 coins, in the second scenario I have c2 coins, where c2 is strictly greater than c1, right? So this is something. Now what I claim is that if I go to a neighbor of this cell I comma j, then I will always have more coins in the second scenario than in the first scenario. So claim is, if we move to a neighbor x comma y of I comma j, irrespective of the direction in which this neighbor is, so it doesn't matter which direction the neighbor is, because for every direction this function is different, right? The operator is different and the value of k might be different, but whatever these values be, the important thing to note here is that all the k values are positive. They are not 0, they are not negative, they are from 1 to 4, right? That's something important. So if we move to a neighboring cell x y of I comma j, and in the first scenario let's say we have c1 prime coins, and in the second scenario let's say we have c2 prime coins, then we can always say that, so basically then c2 prime will always be greater than or equal to c1 prime. So c2 prime will be greater than or equal to c1 prime. And the proof here is pretty simple. Like let's just assume that c1 is equal to 2 and c2 is equals to 4. Then it doesn't matter what the operator is. If the operator is plus, then obviously we will have 4 plus k coins and in the second scenario, and 2 plus k coins in the first scenario. And obviously 4 plus k will be greater. If the operator is multiply, then again it's the same thing. If we are multiplying with some value, then 4k is obviously greater than 2k. If it is divide, then again 2 by k is less than or equal to 4 by k, but it can never be greater than. And similar is the case with minus. So whatever sign we have, it doesn't matter. So if we are coming to a cell I comma j, then we only are interested in what is the maximum number of coins that we had from the cell from where we are coming. So let me write it down. So if we are coming to a cell x comma y, we are only interested in the maximum number of coins that we had in the cell from which we came here, right? So we must have come to x comma y from a neighbor of x comma y, right? But we are only interested in the maximum number of coins that we had in that neighbor, and then we came to that from that neighbor to the cell x comma y. Cool. So this basically hints us towards a dynamic programming solution, and once I write the states of the DP, it will become pretty evident. So the solution will involve dynamic programming, and the states of the DP are also pretty simple. So it's nothing but DP ijk. So DP ijk is nothing but the maximum number of coins that I will have if I reach the cell number I comma j, and I have taken exactly k steps. So maximum number of coins we will have if we reach cell I comma j after exactly k steps, right? So the base condition here is pretty simple, that dp of ar ac and 0 is equal to 0. Otherwise all dp values are initialized to minus infinity, right? Because when k is equals to 0, when the number of steps is equal to 0, then we are at the cell ar comma ac and we can't be anywhere else, so all the other dp values will be in minus infinity, whereas dp ar ac 0 will be 0. And now the constraints, the transitions again are pretty simple. So let's say we know the dp value of ijk. So we know dp ijk, right? So from ijk we can go to any of its 4 neighbors, right? Cool. So first of all, So what we'll do first of all is we will calculate this cost function. So we'll basically implement a cost function where cost of coins and direction will return. So cost of coins and direction will return that currently we have these. So currently we have C coins and we try to move in the dth direction. So cost of C comma D dir. So currently we have C coins and we try to move to the dirth direction. Then what is the new number of coins that we will have? So the new number of coins we will have, if we currently have C coins and try to move in the dirth direction. So this is pretty easy to find out using the information which is given. We just have 4 if statements. I will just show you how to do this. So we just need 4 if statements. So the first direction is north, then the second is east, then the third is west, and the fourth is south. This is in the order the input is provided to us, right? And so now what I am doing is to calculate this cost function, we will just have a look at the operator which is there for the direction. If it is plus, then we simply add k of dr. If it is minus, we subtract k of dr. If it is multiply, we multiply k of dr. Otherwise we have to divide by k of dr, but we need to be careful that if coins are negative, then we need to take ceiling instead of taking the floor. And yeah, so this is the cost function which we can simply calculate. So once this cost function is made, the transition becomes very easy. So now let's say we know the value dp ijk and we want to move to a neighbor. So we know dp ijk and we try to move to a neighbor x comma y in the direction d, right? Let's say that x comma y is the neighbor in the dth direction of I comma j, right? So the transition is pretty simple. So we will go to the cell x y, and if there were k steps before, then the number of steps will become k plus 1 and it will be max of itself. So dp x y k plus 1. And so when we are at ij and we have taken k steps, we know we have dp ijk coins. So after that, the number of coins we will have will be nothing but cost of dp ijk and d, right? So we are trying to move to the dth direction, and that's it. This is it. This is all the transitions that we need to do, and this is enough to basically pass the first test set. So yeah, let's just have a look at the code of the first test set, then we will move forward. Hopefully they provide the code, right? Yeah. So the code goes like this. So we calculate this cost function first of all, right? And then what we do is, yeah. So then basically what we are doing is, this is all irrelevant. Yeah, so we initialize the dp values with minus infinity, as you can see, and all the other dp values are minus infinity, but dp ar ac 0 is equal to 0, right? Cool. I don't know how to look at the full solution. I think I'll have to download it only. So let's just do that, I guess. We can simply open it. Yeah, makes sense. Yeah, so now we can have a look at the full solution. So cool. So all the values are initialized to minus infinity, but dp ar ac and 0 is equal to 0, right? So this is irrelevant. This is irrelevant. Let me just remove all the comments. Cool. So now we just simply we iterate for k from 0 to m minus 1, I from 1 to n, j from 1 to n, and then we iterate for the direction from which we are going from I comma j. So there are 4 possible directions. We iterate on them. So the neighboring cell will be I plus dx of d and j plus dy of d. So this is x comma y. Obviously, if this cell is not valid, it is outside the grid, then we don't go there. Otherwise, what we do is, first of all, we check if the dp value of ijk is equal to minus infinity or not. If that's the case, then we can simply ignore it. Then what happens is we can just do this transition that dp x y k plus 1 is max of itself and cost of dp ijk comma d, and that will just work. Finally, we will iterate over ij from 1 to n, and then we will iterate for k from 0 to m. Notice that we are iterating for k and we are not just taking k is equal to m, because it is allowed to stay at the current cell every minute as well. We don't really have to move at every minute, right? So the number of minutes can be anything from 0 to m, and then we just take the maximum value of dp ijk and that will work, right? So that completes the solution to the first test set, right? Okay, so yeah, there were some issues with my laptop. So yeah, let's continue. So now we were talking about the second test set. So there is just one thing that we need to do to make this work for the second test set. So the only extra constraints that we have for the second test set are that, sorry, this is the third problem. So the only extra constraints that we have is this pizza thing. So there are these P pizzas that we have to deliver. But if you notice that the number of pizzas here are not very much. So there are just 10 pizzas at max, right? So what we can have is we can have one more thing in the state of our DP. So we can have a mask here, or we can keep a subset, right? So in this mask, we can basically keep all the pizzas that we have delivered, right? So this mask will denote, it will be a binary number where the ith bit will be active if we have delivered the ith pizza and won't be active if we haven't, right? Such that we have delivered the pizzas in mask, right? So if you're not familiar with DP using bit masking, then I think you should first learn that. It's not very difficult, but it can be confusing to someone who's just starting out in DP. So get some experience in DP, and then I would recommend go for DP with bit masking. But if you are, then I think this should make sense to you. So we will just add this mask here, and then we will initialize this mask with 0. So DP AR AC 0 0 will be 0, and all the other DP values are going to be infinity. And this mask is initially 0 because we haven't delivered any pizzas, and in the problem statement they have also written that there are no pizzas at the starting point, right? So the mask always will be 0 in the beginning. And now what happens is that we know DP I J K mask, and then we will simply try to move to our neighbor, and let's see what changes are there in the transitions. Okay, so let's just have a look at the code. So what we do is, first of all, for every cell in the matrix, we basically store what is the number of the pizza which is on this cell. If there is no pizza in the cell, then we just store -1. Otherwise, we have a number from 0 to p-1 stored in the cell. And also we have coins, right? So if there is a pizza at a particular cell, we will deliver it and we will get some coins. So at every cell of the matrix, we'll store the number of coins that we'll get. Right, cool. So we have this DP values, and we'll initialize all the DP values with -infinity, but DP of AR, AC and 0 0 will be 0. And then we will iterate from 0 to p-1. We will get the location as well as the coins that we get for the ith pizza. So we will just say that pizza number of xy will be I, and the coins that we get from xy will be C. So now with all that information, then we again iterate for k from 0 to m-1, I from 1 to n, j from 1 to n, and then we iterate on the direction in which we are going. So we are currently on cell I comma j, and we try to go to our neighbor, which is x comma y. If this neighboring cell is not valid, then obviously we'll continue, and then we try to iterate on the mask values. So mask will go from 0 to 2 raised to the power p-1. Cool. So if dp I, j, k and mask is equal to -infinity, we will simply ignore this. Otherwise, there are two cases. So first case is that we don't deliver a pizza here, and the second case is that we deliver a pizza here. Notice that even if there is a pizza in the cell, we can choose not to deliver it right now, right? So there are these two cases, obviously. So first case is that we try not to deliver the pizza. So the new coins will be nothing but cost of dp ijk mask, which are the coins that we have currently, and the direction d in which we are going. And new mask will just be mask because we aren't delivering any pizza. So we will just update this dp value of x, y, k+1 and new mask with the new coins, right? But the second case is that there is a pizza in this cell and we deliver it right now. So pizza number of xy should not be -1, and the mask that we had previously does not contain this bit as active, because that would mean that we have already delivered this pizza. So if there is a pizza here and if we haven't delivered it yet, then new mask will contain this bit. So we will have the bitwise OR of new mask with 2 raised to the power the number of the pizza which is at this cell. And the new coins will also increase by the number of coins, extra coins that we will get on reaching this cell. And then we can simply update the dp values again, dp x, y, k+1 new mask with maximum of itself and new coins, right? So yeah, these complete all the transitions, and then we will just go for I from 1 to n, j from 1 to n, and k from 0 to n as we did for the first test set, and we will initialize our answer with maximum of itself and dp I, j, k and 2 raised to the power p-1. This just denotes the mask that we have delivered all the pizzas, right? Here all the bits are 1. So if final answer is minus infinity, that means it's impossible. So we output impossible, otherwise we output the answer, right? So yeah, this pretty much completes the solution to problem D. So that is all for today. Thank you so much for watching, and I'll see you in the next video. Bye.